you very much, Rafael. And first of all, I'd like to express my gratitude and admiration to organizers, to Rafael and Carlos, of this very interesting and high-level event. Thank you very much, and thank you for the invitation, of course. So, my talk is about, well, it's sufficiently, well, relatively simple equation compared to previous talks, which is the one-dimensional Schrödinger equation. In general, I will consider the potential of the equation being a complex valued function. I'm considering this equation on a finite interval. Omega here is a spectral parameter, can be a complex number. In principle, a more general equation of this type, Sturm-Liouville equation, can be considered here because under certain conditions on P, Q, and R, by the very well-known Liouville transformation, this Sturm-Liouville equation can be reduced to one-dimensional Schrödinger equation. So, first of all, I'd like to speak a little bit about the motivation of this work and talk. I think many of us gave courses on differential equations or partial differential equations or mathematical physics, and we taught the solution of Sturm-Liouville problems, of classical Sturm-Liouville problems, and in fact, when the coefficient here, this Q, is constant, okay, this is a good part of any textbook. But when it is a function, then when it comes to how to solve, for example, such a simple problem, then the only answer is numerical method. Okay, for example, finite differences. What else? So, in fact, what is the usual, let's say, method? How people solve this kind of problem? So, just find eigenfunctions and eigenvalues of this Sturm-Liouville problem on a finite interval. So the usual way is the so-called shooting method. I mean numerically. Okay. Just as in, well, I should tell you from the very beginning that this talk is not about numerical methods. Okay, it's only a part of motivation. So, numerically, how to solve this kind of problems? The shooting method, it consists more or less in the following. So, you fix one value of the spectral parameter, one value of this lambda, which is omega squared. So, for example, lambda 1. And you shoot. You make a shoot. So, what does it mean? You construct a solution which comes out from 0, because the first condition is the solution is 0 in the point A. Okay, and you just construct the solution of a Cauchy problem and obtain something in the end point. Okay, so some value. You see that this value is not 0, and then you need to make another shot. So, for example, you fix the value lambda 2, you do the same, you solve the Cauchy problem, okay? numerically and obtain another value. So, for example, the first value was negative, the second is positive, then there should be some zero in between. And probably the third attempt gives you something close to zero. So you declare it a numerical solution of a numerical eigenfunction. And the corresponding lambda 3 will be a numerical approximation to your eigenvalue. Okay, this is the usual stuff. So what is the difference between the methods for solving Sturm-Liouville problems which are available now? The difference is only how to solve the equation, the differential equation. So how to make these shots, okay? How to obtain the solutions. So, for example, now the best approach, purely numerical approach, is the so-called Prue's method. The Prue's method, which consists in the following. So it's much better, for example, than finite differences. Okay? The idea of the method is just you approximate by polynomials, okay, by polynomials on each small interval, the coefficients of your equation, so your Q. For example, with linear functions, okay, you just approximate it here, then on the next interval, the next interval, the next interval. Then what you do? On the first interval, you have an explicit and exact solution of the approximate equation, okay, with this linear function instead of your coefficient Q. So you write it, this solution. Then it gives you some Cauchy initial values in the next point here. Okay, you obtain some new Cauchy problem. You solve it on this second interval, and then on the third, and then you come to the end, to the end point, and this means that you obtained a solution of your differential equation, an approximate solution. Yes, yes, exactly. So there are many, details in this method, a lot of details, I think hundreds of papers on this method. For example, there is a very nice book by Price, Numerical Solution of Sturm-Liouville Problems, where you can find some information. And what is much more powerful but much more complicated. So if you want to, for example, to try to program, this method is very complicated. It's really complicated. But this package for the numerical solution of Sturm-Liouville problems is available. So you can just download it from the internet. It works well, but it has a lot of limitations, of course. What are the main limitations? First of all, you don't know what it does, in fact. Okay, it's like a black box. Second, for example, it doesn't work with complex valued Q. It doesn't work with, for example, piecewise continuous Q. Okay, it makes mistakes when it comes to problems when you need to compute large sets of eigendata. Okay? For example, 400, 500 eigendata, so eigenfunctions and eigenvalues. In many applications, the main difficulty to apply purely numerical methods is the following. In many applications, you need not just for example, the eigenvalue, but probably the second derivative of the eigenvalue with respect to some parameter. Okay? And this is too difficult to obtain applying purely numerical stuff. For example, I will not speak about this, but for example, when you need the second derivative, when you look for the so-called dispersion coefficient in, for example, waveguides, okay? In fiber optics, for example. Well, so this is like a motivation. I'm not happy with all this, with purely numerical methods. So what I will show to you is a completely another approach. Okay? It's mainly an analytical approach, but it gives better results. As a byproduct of this work, we obtain a very good, very powerful numerical method, and very simple. Okay? So this is what I will talk about. The main ingredient is the transmutation operator. So what is it? Let us consider our one-dimensional Schrödinger equation. On a symmetric interval, it's not important that it is symmetric, it's just for convenience. It always can be done symmetric. So, and I will speak, in fact, this talk is dedicated to one solution of this equation, to the solution which I will call U, which depends on the parameter omega, and which satisfies these initial conditions in the origin. So U in 0 is equal to 1, and the derivative of U in 0 is equal to I by omega. Okay? So when Q is continuous, when the potential Q is continuous, it is a classical, very well-known result that there exists a C1 function, so C1 with respect to both arguments, C1 function K of x and t, such that our solution U is can be represented in this form. Here, what is important? That this is a second order, second kind Volterra integral operator applied to the exponential function. And the most important is that the kernel of this operator doesn't depend on the spectral parameter. This is the main point. So I don't want to speak a lot about the history of the transmutation operator, but some words. So the first work, the first publication where this transmutation, well, not this, where the concept of the transmutation operator in the theory of differential equations appeared was by Delsart, the French mathematician Delsart, in 1938. Then later on, already in 50s, Delsart wrote several papers with Lyons on this subject. So more or less in 1953, 55, more or less in this period, together with Lyons, where they call this operator the transmutation operator. So, but the difficulty with the terminology here is the following: that in the end of 40s already, Soviet mathematicians took this theory, so they developed it a lot. For example, the result that this transmutation operator can be realized in the form of the second kind Volterra integral operator is the result of Povzner, of 1949, and later on many Soviet mathematicians worked with this concept. So, for example, Levitan, Marchenko, of course, Gelfand, many others. I cannot here give all the list. And they called it the transformation operator. A very boring term, in my opinion, because the transformations are many concepts in mathematics are called transformation, and transmutation is something romantic. It comes from alchemistry, when the medieval alchemists looked for a philosophical stone to turn cheap metals like plumb into gold. So in fact, we will do something similar here. This operator is doing precisely this. It turns the cheap exponential function, which is available even on small calculators, okay, now, and turns it into solutions of a quite complicated equation. Okay, to the difference from the alchemists, we also are interested in the inverse operator, because the alchemists just plumb to gold and that's it. Why to come back? But we are interested in the inverse operator and in good properties of the inverse operator. And in fact, and in fact, the result of Povsner, that the operator can be realized in this form, best possible form, in fact, the second kind Volterra integral operator, precisely gave this immediately, that the operator is invertible and the inverse is bounded. Okay? Of course, in a convenient space. Here it's not difficult to introduce the convenient space. So more about precisely this transmutation operator can be found in the first chapter of the very well-known book by Marchenko. For example, in the very good book by Levitan on inverse Sturm-Liouville problems, in a recent review paper by Sitnik, unfortunately it's only in Russian, but well, some people can read it, and and in many other books, in fact. Okay. So first of all, the condition on Q can be substantially weakened. For example, there is a work by Grenev, they are Ukrainian mathematicians, Grenev and Mikityuk, of 2004, where they proved that everything goes well for the potential Q from this Sobolev space W2 minus 1, which is which contains already some quite nasty functions, like for example the Coulomb potential, or for example they can be piecewise continuous. In this case, what the only change is that the kernel of this transmutation operator is not anymore a C1 function, but it will be an L2 function. Sorry? No, it's okay. Everything is okay here with that. So, okay, so in fact, in my talk, this will be the assumption. Q belongs to this W2 minus 1. Now, when Q is C1, and so very smooth function C1, then we can say the following, that the integral kernel K is a unique solution of the Goursat problem. Okay, this Goursat problem. So what does it mean? Here we have a hyperbolic equation, okay, and on the diagonals, when t is equal to x, our function is defined by this integral, okay, and when t is equal to minus x, it's just 0. So what does it mean? That in fact this kernel K leaves. So if this is x, so we need to solve this Gursa problem in this domain. And on these characteristics, we have our function given. The problem is that to solve this problem, this Gursa problem, in general, even numerically, is quite difficult, and the difficulty is comparable with the solution of the spectral problem. And here it's important that it's only for C1 functions. Okay, you can give some sense to this same Gursa problem when Q is just continuous. Okay, but if it is worse than continuous, then it's difficult to introduce the corresponding partial differential equation. Okay. So in fact, I will not need it here. This equation, I will not need it. I will need just this Gursa data on the characteristics. Okay. So now what we will do, we will construct this kernel K. So what can I say? This, in fact, this transmutation operator or transformation operator appears in hundreds of publications, okay? But appears mainly as a theoretical tool. So it exists. It exists in such a nice form of a second kind Volterra integral operator, and that's it. This is what is used mainly. There were quite a few works where people tried to construct it. So, for example, the first such work, but I'm sure that there were earlier works. The first such construction I found in an early book by David Colton. There is a book of 70-something, his first book, which is, well, almost has no citations. I don't know, because his books starting with theory of partial differential equations and so on, they are very well known. But that one, in fact, almost no citations. So there is an attempt to construct this kernel just by successive approximations. And there are some other works where people, in fact, what try to do is to solve this Gursa problem. So this is not our method. We take another way here. So the first important thing, and I think this is the most difficult slide of this talk. So please pay attention. So the first important thing here is to construct the so-called formal powers Vk. So let us suppose that somehow we know a solution of this problem, this Cauchy problem. So omega here is 0. We just take a solution of this equation which satisfies these initial conditions. Okay? So for example, we construct it numerically. Doesn't matter how. Then we start to do the following. So we construct two systems of functions, x and x tilde. How we do it? So for example, pay attention at x. x 0, the first of these functions x, will be just 1. So on each next step, we take the result of the previous step, multiply it or divide by this f squared, okay, and integrate. This is what we do. And to construct the other system of functions, x tilde, we do the same but in another order. Okay, that's it. And then from the first system of functions, we take just only the odd. and from the second only the even. Multiply them by our f and obtain a family of functions phi k. Okay? This will be called the formal powers. And they are the main ingredient of what we will do here. So these functions, now I will explain what they are, in fact. But first of all, as it is important to construct them, really to construct them, for example, numerically, it's very easy to construct hundreds of these functions without any problem, because the recurrent integration is the best possible numerical operation. Is much better, for example, than the linear combination. Okay, because it doesn't each step doesn't add any new error in theory. Okay. Now, but here the natural question you can ask: what happens if f has zeros? Okay. Because nobody told us that a solution of this problem will not have zeros. Of course, it can have zeros, and in such case, some of these integrals will not make sense. Okay, but the functions phi k themselves, they will make sense anyway, and in such case, just they can be constructed in another way. I will try to explain it quickly now. So, just take any solution of this equation which satisfies this initial condition and which has no zeros at the interval. Such solution always exists. Okay, this is proved. For example, well, the proof which I know is in our paper with Mike Porter of 2010, and in fact in 2011 there is a publication by Italian mathematicians where they prove a similar result, but in a more general setting for n-dimensional, for n-order equations. Okay? Probably this result is not new, I'm not sure, but we didn't find it. So such solution always exists. For example, when q is real value, this is trivial. To construct such a solution, you just take our f from the previous slide and f1 which satisfies these initial conditions. So one was 1, 0, and this one is 0, 1. So if you take this combination of them, this is by the very old theorem proved by Sturm himself about the alternating zeros of the solutions of the Sturm-Liouville equation. This will not have zeros, this g. So just take this g. Then you construct, following the same scheme from the previous slide, the formal powers phi k capital, which correspond to this g, okay, to this function g, and then our phi k small will be just this phi k capital slightly changed. So in fact, what this slide means, what this formula means, that essentially they are unique, these formal powers. So it seems that you take another solution of the equation, okay, and you obtain a completely another system of functions, but it's not the case, in fact. So you see that the odd, they will always coincide, and it's easy to see it. And the even, they are related in this way where there is a constant in between. Yes, precisely. But you know, it's difficult to see it directly. But it's very easy to see it in this way. So this phi k, they always have sense, and they can be constructed this way. Okay, so what is the meaning of these formal powers Vk? The meaning is very simple. We are talking about our favorite solution. Okay. So this solution can be represented in this form, okay, where this is just a power series with respect to the spectral parameter, and the coefficients of this power series, of this Taylor series, are just our formal powers Vk. Okay? So it's very simple. In this form, I can tell you the following, that these formal powers, in fact, in different forms, okay, they arise from time to time in different papers. But at least in this form, they appeared in this paper of mine in 2008, and later on in, well, I could put here the heart of Juicy here, because in this second paper the explanation is much easier and doesn't require difficult stuff. Okay, that was done together with Mike Porter. So we call this representation of the solution the spectral parameter power series. Okay, so this is our solution of the Sturm-Liouville equation. But it's not always the best form to construct the solution. So I will show you 3 more forms which in a sense are better. Okay? So for us in this talk, this theorem, spectral parameter power series, will be the auxiliary result, in fact. Okay. So in fact, what does it mean? You know, this spectral parameter power series. It's very easy. So you take our favorite solution U. We know that this solution is just the transmutation operator T applied to the exponential function. Okay? Now T is omega independent. So what does it mean? That in fact this spectral parameter power series is equal to this series where we just apply T to each power of X. Okay? So from here, as they are just two power series with respect to omega, and they converge uniformly, so the coefficients have to coincide. So phi k coincides with T applied to xk, and we obtain what we call the mapping property of the transmutation operator. So T applied to x to k is just our function phi k, which we know how to construct in this tricky way with the recurrent integration. In particular, what does it mean to apply T to 1? It means that we obtain our solution F, our particular solution of the equation without omega, with omega equal to 0. Okay? So this mapping property was observed in this paper together with Hugo Campos, who was my PhD student at that time, and Sergei Torba, which is my Mexican colleague in Querétaro. Okay. So please, if you have questions, don't hesitate. Okay, what does it mean, this result, in just some other terms? Okay, look at this. So T applied to xk is our phi k. Let us write it explicitly. What we obtain? We obtain that this scalar product of the kernel k with any non-negative integer power of t, okay, this scalar product in L2 is known. Is known because it's just our formal power phi k minus x to k. So this is in fact a classical problem of moments. which can be solved, fortunately, in this case, in the following way. So when we want to solve a problem of moments, one of the possibilities is to use at least this hamburger problem, is to use the orthogonal polynomials corresponding to the model, to the problem. So here the best choice, possibly the best choice, is are the classical Legendre polynomials. So the Legendre polynomials, they are orthogonal on the interval -1, 1. Okay, and here we have the interval -x, x with respect to t. Okay, this means that it's convenient to took not just Legendre polynomials, but the Legendre polynomials of t over x. This gives me an orthogonal basis of L2, okay, on this interval -x to x. Now, so we can look for a Fourier Legendre series representation for our kernel K, just some quite standard stuff. So here, with respect to t, we have these Legendre polynomials, and the coefficients, which of course depend on x. Just for convenience, we divide over x. Just for convenience, it's not important. So these coefficients beta n should be found. To find them, we have our mapping property. So we know how are the scalar products of our kernel K with every power of t, which means the following, that we know already how the transmutation operator acts on Legendre polynomials. Okay, and this is sufficient to construct the coefficients. So the kernel K has this form where the coefficients beta can be constructed using our formal powers Vk, and here L, K, N are just the Legendre coefficients, the coefficients from the Legendre polynomial. So the case coefficients, the case coefficient of the n-order Legendre polynomial. Okay. So this series converges with respect to t in the L2 norm. If Q is continuous, then the series converges uniformly. Okay. And in this work, together with Luis Navarro, who was a postdoc, he is from Venezuela, and he made a postdoc with us in the CINVESTAV, and with Sergei Torba, we obtained, besides this representation, we obtained a much more detailed estimates for the convergence rate of this series. So they can be found there. Okay, so what happens if now we use this Fourier Legendre representation of our kernel? Okay, so we just take our kernel K in the form of this series and put it into the transmutation operator. Okay, so we do it, and then what happens? We need to just to evaluate these integrals, the Legendre polynomials, by the exponential function. It's just after a small change of variables, okay, from -1 to 1. These integrals are very well known, and we obtain here that our solution U, okay, is just this exponential plus the series which are, with respect to the spectral parameter omega, are spherical Bessel functions. Okay. So with the same coefficients beta n here. The spherical Bessel functions are defined in this way. This is a very well-known special function. And the series converges uniformly with respect to x, and as I told you, there are much more detailed convergence rate estimates for this series. So, but why it is interesting? Now I would like to explain it. So it's interesting because behind of this result we have the transmutation operator. What I want to say. So take, just for simplicity, take omega real and different from 0, and consider a partial sum of our Fourier-Legendre representation of the kernel, okay, the truncated series. So we obtain some approximation of our solution, un, okay, which is given by this formula. Now, if we want to estimate the difference between u and un, we find the following. So we just apply here, for example, the Cauchy-Bunyakovsky-Schwarz inequality, okay, and obtain that the difference is less or equal than the norm of the difference between k and kn, okay, and by the norm of the exponential function. Okay, this is simple. From here we obtain the square root of 2x from here, and this we call epsilon n of x. Okay, but the most important point here that nothing depends on omega, because the kernel is independent on omega. Okay, so what we obtain, that the difference between the approximate solution and the exact one, it in fact doesn't depend on the largeness of spectral parameter. Okay? So when we calculate the solution of our one-dimensional Schrödinger equation, it will be the same for us if omega is small or if it is large. Okay? I will show you a numerical illustration of this just a moment. So more generally, when omega is complex, but we suppose here that it belongs to some strip, imaginary part of omega is less or equal than c, some constant, then the estimate looks like this, but it's it's independent on the real part of omega. So the same thing, okay? For numerical solution of Sturm-Liouville problems, at least for classical Sturm-Liouville problems, there is a result which I don't want to give too many details, but even when Q is complex, the complex eigenvalues are in fact in a strip, okay, and this strip can be evaluated. Estimated on a complex plane. So this works well in this situation also, when Q is complex. Okay. So how it looks like when we apply it on the computer? Because one thing is theory and another one is computer. Completely another world. So let us consider, for example, this, which is called first Payne problem. Payne is his surname. It doesn't mean, well, it shouldn't be translated. So the problem is not so painful. Okay, I would like to say. So just find the eigenvalues and eigenfunctions of this problem. Okay, where Q is just the exponential. Why this problem is good? Because the exact eigenvalues are known. So this is very convenient. So here, what we did, we took 29 just terms in our this series. Okay, I mean this n is 29 here. Why 29? I will explain later. It's very easy to see what is the optimal n which can be chosen. In fact. So only 29 terms, which is a very small number. Now this graph, so for example in blue is the absolute error of the first 100 eigenvalues of this problem, computed with the aid of our representation. Okay, this is the so the most important number here is of course this minus 11. Okay, 10 to minus 11. This is the absolute error. It's completely uniform, as predicted by theory. And this the relative error of the first 100 eigenvalues, which is at the level of machine precision. Now, this graph is the same, but for the next 400 eigenvalues. So, the absolute error of the next 400 eigenvalues. The relative error of the next 400 eigenvalues. So, the error is completely uniform as predicted by the theory. Okay? And we can continue, of course, it's not a problem. So all this calculation took 1.5 seconds. So this is why it's interesting. Okay? So I can tell you that no purely numerical method can give you something similar. Okay? Now, so what if we don't apply, for example, Legendre polynomials? What if we apply some other system of polynomials? How can we do it? So here the idea is very simple. So we just can extend our kernel K by 0. Okay? For example, as it is here, it is shown here. So when t is from minus infinity to minus x, then we just declare that our kernel is 0. Okay? Then this function is defined from in t, from minus infinity to x, and we can apply the system of Laguerre polynomials to obtain a representation for our transmutation kernel. So how we do it? There are small tricks which are very simple, just changes of variables. So the Laguerre polynomials live from 0 to plus infinity. Then we need to make a small change of variables. So instead of our kernel K, we consider this one. And already this auxiliary kernel, small k, it will belong to the space L2 from 0 to infinity with this weight, equipped with this scalar product. This function admits the Fourier-Laguerre expansion, so it will be convergent in the corresponding norm of this space. So we can look for the coefficients an of this Fourier-Laguerre expansion. So more or less in the same way as before, just the other system of polynomials. We obtain the coefficients an in this form. So also our formal powers phi j minus xj multiplied by a polynomial. And then we do the same. We substitute the kernel in this form, in the form of the Fourier-Laguerre series, into the transmutation operator, and we evaluate the integrals which arise there. Okay, so the integrals are very simple, and we obtain the following representation of our favorite solution. So our U has now this form. This is the same, of course, U, but we could write it in another form with these coefficients an, okay, and multiplied by this fraction. Now, as everything is constructed with, using the transmutation operator, the same thing happens. So if we consider the partial sum, here un, then we obtain that an estimate which is independent of omega. In the same way, it's just Cauchy-Bunyakovsky, just in another L2 space. Okay, we obtain the same estimate. Not exactly the same, but also independent from omega. And also on the computer, it can be seen how it works. Okay? So more or less the same way. And here, when omega is complex, then we obtain this estimate, which is also independent of the real part of omega. Okay? And in fact, it's very easy in every case, every considered case, to construct another way to obtain the coefficients of the expansion. When you know what you are looking for, then you just put it into the differential equation and obtain some nice system of equations which can be solved very easily. So, for example, for the coefficients an, the system is like this. So every new an is constructed using the previous one, okay, and with these initial values, and it means that for numerics it can be obtained as using this recurrent integration, which is a very nice operation. So in fact, on the computer we could construct here tens of thousands of the coefficients an. So nobody needs so many, but in fact no problem to do it. So this is in this recent work, the last year. And now, of course, we can extend it, our kernel, also to plus infinity by 0. And then from minus infinity to plus infinity, we have Hermite polynomials, of course. A very nice system of orthogonal polynomials. So, in this case, we can construct the series expansion of our kernel K in this form, where Hn are very well known Hermite polynomials, okay, with this weight, and multiplied by the coefficient Cn, which we should find now. Okay. We find them in the same way as I explained before for the Legendre polynomials and for the Laguerre polynomials. So we obtain the following: that the coefficient Cn admit this representation. Here we have the coefficients from the Hermite polynomials, which are well-known numbers, by the difference between the formal power phi k and x to the power k. So these are our coefficients Cn. For example, C naught will be this guy, T1 this guy, and so on. And for the next step is to put this representation of our kernel, already the Fourier-Hermite series, into the transmutation operator, and to see what's going on with the solution, with U. So we obtain the following. So our the same solution U is the same exponential plus, in this case, this integral. Okay. Now we evaluate these integrals and obtain this nice result. So our solution U is represented in this form. You see here these coefficients e to minus omega squared over 4, which is very convenient for working with large omega. And Cn are very easily constructed. And as in the previous cases, we have these estimates independent of omega. So you take the partial sum, un, and you obtain already for complex omega in a strip, okay, you obtain this kind of estimate, which is, as before, independent of the real part of omega. Okay? So, at least you saw 4 ways to write down the solution of the one-dimensional Schrödinger equation. The first one was more or less like a Taylor series, which works well when omega is very small. Okay? But the other 3 work pretty well for very large omega and really are useful for numerical calculations. Now, okay, so this coefficient C can be constructed, Cn can be constructed also by recurrent integration, which comes from here. And just to summarize what we saw up to now, so the first representation was the spectral parameter power series representation, this form, which is just the application of the transmutation operator to the Taylor series of the exponential function. Okay? The second was the Fourier-Legendre expansion of the kernel K, which leads to the series for U in this form. By the way, I forgot to tell you that this kind of series appear in analysis not in differential equations, but they are known just in analysis as Neumann series of Bessel functions, when what is changed is the order of the Bessel function. Such series are called Neumann series of Bessel functions. The book of Watson of 1922, there you can find it. Now the third representation, the Fourier-Legendre representation for the kernel, and the corresponding representation for the solution was of this form. And finally, the Fourier-Hermite expansion for the kernel leads to this form of the solution of the Sturm-Liouville equation. Well, I wanted to tell you some things, but I will not do it. I understand that it's already 7 o'clock. Okay, so just to mention that in fact the applications are not only to one-dimensional Schrödinger equation. For example, if we want to construct complete systems of solutions of partial differential equations which admit some kind of symmetry, for example, when the coefficient depends on just one Cartesian variable or one cylindrical variable, or etc., etc. These results allow us to do it. So, for example, for this kind of equation, so you take here the Laplacian in 2 dimensions, for example, and Q depending only on one Cartesian variable, then you can construct a complete system of solutions just to apply, for example, the transmutation operator T to harmonic polynomials. Okay? You obtain a complete system of solutions which can be applied also in numerical calculation and all this stuff. So, for example, the result of application is just to change the powers of x by our formal powers phi, pk. And, for example, the well-known method of fundamental solutions also can be generalized onto the case of such partial differential equations admitting symmetry in their coefficients. So, in fact, the transmuted fundamental solutions can be constructed. They can be used for numerical applications. So thank you very much for your attention. We have at least the SPPS we have for it. So I'm not a specialist in this zero-dimensional stuff. In fact, I started with n-dimensional mathematical physics with Clifford algebras, then quaternions, then pseudo-analytic functions in 2 dimensions. Then I came to 1 dimension. So I have one work on zero-dimensional stuff. Where we precisely construct the spectral parameter power series for Jacobi operators. Okay, but all other things like the transmutation operator and all this, I don't know. Investigate it. Thank you.